Picture a sheet of paper scattered with points from two groups, the gold ones and the blue ones. Your whole job is to draw a single straight line that keeps them apart. Start with a bad line, one that cuts right through the wrong points. Every time it gets a point wrong, you nudge it, tilt it, slide it, until the two colors finally sit on opposite sides. That simple idea, score, decide, and when you're wrong, move the line, is the perceptron, the oldest, simplest artificial neuron, and the seed of every neural network that came after it. Here's the neuron in two small steps. First, it takes your inputs, weights each one, and adds a bias. Weight 1 times input 1 plus weight 2 times input 2 plus b. Call that running total z. The score, written compactly, z is w dot x plus b, the same weighted sum you met in linear regression. So far, nothing new. The magic is in what happens to z next. The score goes through a hard switch, the sine function. If z is above 0, the neuron fires plus 1. If it's 0 or below, it fires minus 1. No maybe, no in between, a blunt yes or no. That output, y hat, is the prediction. And notice the two labels are plus 1 and minus 1, not 0 and 1. That symmetric choice is what makes the learning rule fall out so cleanly, as you'll see in a moment. Where exactly does the neuron flip its answer? Right where the score z is 0. On one side z is positive, and it says plus 1. On the other side z is negative, and it says minus 1. Set the score to 0 w dot x plus b equals 0. And because that equation is linear in the features, it traces out a perfectly straight line across the plane. That line is the decision boundary. Drop the points on, and you can see it. Gold on one side, blue on the other, split by a single straight cut. So the perceptron is a linear classifier. It can only ever carve the plane with a straight line. And there's a lovely geometric fact hiding here. The weight vector w always points straight out, perpendicular to the boundary. It is the line's normal, aiming into the positive side. Turn w, and the line turns with it. So how does the line move itself into place? By one small rule, applied only when it gets a point wrong. The new weights are the old weights, plus eta times the error times the input x. And the bias shifts by eta times the same error. Eta is the learning rate, a small positive step size that controls how big each nudge is. And the error is y minus y hat, the true label, minus what the neuron guessed. Here's the beautiful part of choosing plus and minus 1. When the neuron is already right, y equals y hat. The error is exactly 0, and nothing moves. Correct points are left alone. When it wrongly calls a positive point negative, the error is plus 1 minus minus 1. That's plus 2. So we add a positive multiple of x to w, which pushes that point score up toward the positive side. And when it wrongly calls a negative point positive, the error is minus 2. We subtract a multiple of x, dragging that point score down, back toward the negative side. Every mistake tugs the boundary the right way. Now let's actually run it. 8 points, gold positives on the right, blue negatives on the left, and a first guess of a line that clearly gets several of them wrong. I'll feed the points in one at a time. Whenever the line misclassifies one, watch it tilt and slide. That is the update rule, working geometrically. Keep your eye on the moving line. The first gold point on the right is wrongly on the minus side, so the line swings toward it. Another gold point is still misjudged. Nudge again, and the line keeps tilting upright. Now a blue point sits on the wrong side, so this time the line leans back the other way. A gold point slips through once more. One more small correction, and a final tug from a blue point. Watch what happens next. And there it is. After just 5 corrections, every gold point sits on one side and every blue point on the other. The line found itself, no calculus, no gradient, just 5 honest mistakes and 5 small nudges. Will this always succeed? It depends on one property of the data. We call a dataset linearly separable if some straight line, some single hyperplane in higher dimensions, can split the two classes perfectly, with zero mistakes. And here is the promise that made the perceptron famous, the convergence theorem. If the data really are linearly separable, the perceptron is guaranteed to make only finitely many mistakes, and then stop, sitting on a line with zero training error. It will always find a separator if one exists. But if the data are not separable, if no straight line can ever split them, the algorithm never settles. It keeps finding a misclassified point, keeps nudging, forever chasing a boundary that simply isn't there. But some patterns defeat a single line entirely, and the classic one is XOR, exclusive OR. The answer is positive when the two inputs differ, and negative when they match. Plot those four corners. The two positive points sit on one diagonal, the two negatives on the other. The classes are diagonally opposite. They interlock. Now try to separate them with one straight line. Tilt it any way you like. Every single line leaves one point stranded on the wrong side. No line on this plane can ever do it. This was the wall that stalled the field for years. The escape is to stack neurons in layers, feed several perceptrons into another. Two straight cuts can bend around a corner. Many layers can carve almost any shape. That single idea grows straight into the neural networks we use today. Let's turn the crank with real numbers. Weights -1 and 1, bias 0, learning rate 1/2. The point is 2, 1, and its true label is positive. First, the score. -1 times 2 is -2, plus 1 gives z equals -1. That's at or below 0. So the neuron fires -1, but the truth was positive. A mistake. So the error is +1 minus -1 plus 2 times the learning rate 1/2. The whole step multiplier is 1. Update the weights. -1, 1, plus 1 times the point 2. 1 gives 1, 2. And the bias, 0 plus 1 is 1. Now trust nothing. Recheck the very same point with the new line. 1 times 2 plus 2 times 1 plus 1 is 5. 5 is above 0. So this time the neuron says positive. The point it just got wrong is now right. One more. This time a negative point misjudged. Weights start at 0, bias 0.5, learning rate 1. The point is 1, -2, and its true label is negative. The score is just the bias, 0.5, which is above 0. So the neuron fires positive. Wrong again. The truth was negative. The error is -1 minus +1, -2, and times eta of 1, the step is -2. Update 0, 0 plus -2 times 1, -2, gives -2, 4. The bias, 0.5 plus -2, is -1.5. Recheck. -2 times 1 is -2, plus 4 times -2 is -8. -1.5 more, -11.5. Comfortably below 0. So the neuron now correctly says negative. Both mistakes fixed. Your turn. Weights 1 and -1. Bias 0. Learning rate 1. Take the point 2, 2, whose true label is positive. Pause the video, classify it, and if it's wrong, do one update by hand. I'll wait. Here's the walkthrough. The score is 1 times 2 minus 1 times 2 plus 0. Exactly 0. 0 counts as the negative side, so y hat is -1. But the truth was positive. A miss, so the error is +2, and with eta 1 the step is 2. Update the weights. 1 -1 plus 2 times 2, 2, gives 5, 3. The bias becomes 2. And the check, 5 times 2 plus 3 times 2 plus 2 is 18, safely positive. If you landed on 5, 3, bias 2, you've genuinely got the rule. Trap 1. Expecting too much of one neuron. A single perceptron can only ever draw a straight boundary. Anything curved, anything like XOR, is beyond it. You need layers. Trap 2. Assuming it always stops. Convergence is guaranteed only when the data are linearly separable. If they are not, the perceptron loops forever. So in practice, you cap the number of passes. Trap 3. Mixing up the labels. The tidy update rule assumes +1 and -1. Swap in 0 and 1 and the error term, and the whole geometry quietly changes. And trap 4. Forgetting the practicalities. If one feature dwarfs the others, or the learning rate is too large, the boundary swings wildly and takes ages to settle. Scale your features. Keep eta modest. Let's lock it all in. The perceptron is a single neuron. It takes a weighted sum z equals w dot x plus b and slams it through the sine function to a hard plus or -1. Setting that score to 0 draws a straight decision boundary, a line whose normal is the weight vector w. The perceptron is, at heart, a linear classifier. It learns only from its mistakes. On every misclassified point, nudge w by eta times the error times x and shift the bias the same way. Correct points, it leaves untouched. If the data are linearly separable, it's guaranteed to converge. If they're not, like XOR, one line can never do it, and you stack neurons into layers instead. That small step is where deep learning begins.